So this is part 2 of the topic popular matchings. So we stopped at the slide where we said we know how to find a maximum size popular matching, and it has a size guarantee of at least 2/3 the size of a maximum cardinality matching. So maximum cardinality matching. So there are applications where, well, every vertex has a strict preference order and so on. Those preferences are of great importance, but what is of even higher importance is the size of the matching. So there are applications, very natural applications, assigning medical students to hospitals for their residencies during a pandemic like the COVID pandemic, where doctors had to be assigned to hospitals. The cardinality of the matching is of utmost importance, and in fact this has been studied by people way before. In fact, we are talking about it now in the context of popular matchings, where you need to assign accommodation to sailors when they come inland, and everybody has to get accommodation. So size of the matching is of great importance. So sailors have preferences over in what sort of accommodation they want to stay, and accommodation hosts have preferences on which sailors they would like to have. Irrespective of their preferences for each other, the size is really the most important aspect of a matching here. So here the set of feasible or admissible solutions. So that's the set of all maximum matchings. Actually, something seems to be a little wrong, right? Every slide is coming twice. And our goal is to find a best maximum matching. So it's not the entire set of matchings that is the set of admissible solutions. It is only the subset of maximum cardinality matchings that is a set of admissible solutions. Within admissible solutions, we want to find the best one. So we want to find a best maximum matching, where the definition of best is as per vertex preferences. So a very natural definition is the following. How about a maximum matching with the minimum number of blocking edges? Pallavi was also talking about this problem, and as she said, finding such a matching is NP hard. So this was already considered so many years ago by Biro, Manlove and Mittal, and they showed it's NP hard. So since we are in the realm of popular matchings, how about a maximum matching that's popular? Well, there need not be any maximum matching that's popular. So we came up with a size guarantee of 2/3, that is the size of a largest popular matching is at least 2/3 the size of a maximum cardinality matching, and that's tight. If you look at this example, where I've given this 1 is top choice, 2 is second choice, 3 is third choice. So if you should examine this carefully, you will see that the blue matching is a popular matching here. So this has nothing to do with the blue red colors that we used. I just used blue independently here. The blue matching is a maximum size popular matching, and this instance does have a perfect matching. That's the red matching. So there is a size 3 matching, but a largest popular matching has size 2, and there is only one size 3 matching here, the red matching, and that's not popular because the blue matching defeats the red matching. So if you ask for give me a maximum cardinality matching that's popular, the answer is there is no maximum cardinality matching that's popular, because there is only one maximum matching and that's unpopular. But since the set of admissible solutions for us is the set of maximum matchings, maybe we should not compare the red matching against all matchings, in which case it is getting defeated by some matching, but let's compare it only against maximum matchings. So let's ask for a maximum matching that does not lose an election to another maximum matching. It's okay for it to lose elections to smaller matchings, but smaller matchings by definition are even unacceptable solutions. They are infeasible solutions. So we don't really care. Even if an infeasible solution is more popular than a maximum matching, by definition is infeasible, well, it does not even matter whether our matching loses to such a matching or not. As long as it does not lose to another maximum matching, we are happy. But why does such a nice maximum matching need to exist? As we saw in the last lecture, we are asking for a weak Condorcet winner, where the set of candidates is not the set of all matchings but only maximum matchings. When we looked at the entire set of matchings, we used garden force result, that every stable matching is popular because stable matchings always exist, popular matchings always exist. But now if we shrink the size of candidates to only maximum matchings, maybe back to the old weak Condorcet winner kind of cycles, maybe there are always cycles here. So this is a valid question. Does such, let's call them popular maximum matching. So maximum matching is to be considered as one phrase. A popular maximum matching always exists. Is it always the case? And even if it always exists, maybe it's hard to find one. Is it easy to find one? These are the questions we'll consider for the first half of this talk. So we'll take inspiration from the red-blue graph that we constructed in the last talk. Recall that graph where every edge had two copies, red copy and a blue copy. Suppose we extend this idea. What does extending this idea mean? Any guesses? Wonderful. Suppose we use n colors. So n is the number of agents, the size of the set A. Why just restrict ourselves to only two colors? Let's have n number of colors, red, blue, green, purple, cyan. I used whatever I could. And for every agent we'll say, as we said before, red is better than blue, blue is better than green, green is better than magenta, magenta is better than cyan, so on and so forth. And how do we do it for jobs or vertices in the set B? Fantastic. Let's do it the other way around. So cyan is better than magenta, better than green, and finally blue, then red. And within any color class is the original preference order. So let's construct this colorful graph where every edge has n copies in n different colors, and let's run Gale-Shapley algorithm here. So agents propose, jobs dispose, find a colorful matching m star, just ignore the colors, that's our matching m. And interestingly turns out this m is a maximum cardinality matching. Moreover, m either wins or ties with every maximum matching in the graph. So this is exactly what we wanted. There always exists a popular maximum matching. Just the same idea as we had in the last lecture, but just let's be more colorful. And so it always exists and it can be computed easily by this algorithm. So it takes n times the size of, it takes n times the cardinality of, n times the complexity of the Gale-Shapley algorithm, because we are running it in this multi-graph where every edge has n copies. So is the algorithm clear? And so this is an order mn running time, and we always have such a matching. It's a constructive proof that such a matching always exists. So how do we prove it? I've just made a couple of claims. Why are these claims correct? Let's go back through the exercise of proving our claims. So recall this edge weight function that we used. So the weight of an edge is one of the three values, 0, +2, -2. It is the sum of the votes of the endpoints of the edge for each other versus the respective assignments in M, and the vote is either +1, -1 or 0. And just as we did for in the case of maximum size popular matching, this observation is easy to see. If the weight of every maximum matching under this edge weight function is at most 0, then M is a popular maximum matching in the graph. So let's go back to writing LPs. Let's write the linear program for maximum weight, maximum matching. There are two maximums here. So we are not insisting on a perfect matching. I have not put any self loops here if you have observed. So we want to find every vertex can be matched along at most one edge, that's this constraint, and we are interested only in maximum matchings. K is the size of a maximum matching. So this constraint says the sum of, for all the agents, if you sum this, then there are k edges. So this is, so these constraints capture that the feasible region is basically the extreme points are all the maximum matchings, and we want to find a maximum weight maximum matching. That's what the objective function is capturing. And the optimal value of this LP is at most 0, means every maximum matching has weight at most 0, which means our matching M is a popular maximum matching, because we said, in fact, this weight function being at most 0 implies, so that was our observation. So these things you can easily check on your own, so I am rushing through it. Let's take the dual, the same method that we did last lecture. So the dual variables, we have an extra variable here, z. Where did this z come from? It corresponds to this new constraint that we had. So the alpha a's and alpha b's correspond to these constraints, and now we also have the restriction that alpha value has to be non-negative, because earlier we had an equality here because we put self loops and that allowed alpha to be unconstrained. Now because I didn't put self loops, we still have less than or equal to, so alphas have to be non-negative, but this is an equality. So the corresponding variable z, that's unrestricted. Our goal is to show the optimal value of the dual LP is at most 0. So our goal is to show a dual feasible solution. This is almost the same as last time, however, we have an extra variable z here, and of course alpha u's are constrained to be non-negative, and the objective function here is k times z plus, as before, summation of all the alpha u's. So basically our matching was obtained as a stable matching in this colorful graph. So rather than call the colors red, blue, green, so on, let's say red is 0, blue is 1, let's use numbers, color 0, color 1 till color n minus 1 to denote the n colors in the G star graph. So let's again do a partition of the vertex set as we did in the last talk. So let AI be the set of agents who are matched along color I edges. So A0 will be the set of agents matched along color 0 edges, that was like red edges in the earlier talk. A1 will be the set of agents matched along color 1 edges, that was the red blue edges in the previous talk, and symmetrically BI is the set of jobs matched along color I edges. So those were again like B0, B1 in the last talk, but now I have n such partitions. So this picture will be useful here. A0, B0, A1, B1, finally An minus 1, Bn minus 1. So, and let's put unmatched vertices of A in this top left and unmatched vertices of B in the bottom right. So this is a partition of the vertex set we have got based on this stable matching M star in the colorful graph G star. So is this partition okay? So there are nice properties that will hold just by the stability of M star in G star. So the way we have defined the preference orders, because within each color class the order of preference is exactly the same as the order in the original graph, it will be the case that the matching M restricted to each set AI union BI is stable. And when we look at an edge that goes one level downwards like this, from AI plus 1 to, from little a in AI plus 1 to little b in BI, the weight of such an edge has to be minus 2. This is the same argument as we saw in the last lecture for any edge between A1 and B0, where we proved that weight of the edge is minus 2. It's the same proof all over again. Now we have even more levels, and we show it's easy to again justify. There is no steep edge. By steep edge we mean from A2 to B0 or A3 to B1. There is no edge between AI and Bj where I is at least j plus 2. So again this follows from stability. If there is such an edge, there will be a blocking edge, and also there is no augmenting path with respect to our matching M. If there is an augmenting path, there is a path from the top left to the bottom right, in which case we'll show that there are at least n plus 1 agents that participate in the augmenting path, but the number of edges is only n, number of agents is only n, so there is no augmenting path. So any augmenting path will have to go between every successive levels actually, because there are no steep edges, and so it will end up having n plus 1 agents, which is one too many agents, so there is no augmenting path. So this property that there is no augmenting path with respect to our matching M implies M is a maximum cardinality matching in the given graph G. And we also need to show a dual feasible solution to prove all the properties that we wanted, that is a popular maximum matching. So let's set the values Z and the alpha values as follows. Let Z was unrestricted. So take Z to be minus 2 times n minus 1 and take alpha A to be, it looks a bit contrived, how did you come up with this value, but it's just so that Z plus alpha A will always be minus 2i and alpha B will be plus 2i. So we come up with this assignment of alpha values, and this will immediately ensure that unmatched vertices are always in either A n minus 1, the top left, or in bottom right, that is B0. And this assignment of alpha values will ensure that alpha u is 0 for all these vertices. And our constraint was to show that alpha A plus alpha B plus Z was at least some weight of the edge, and we also wanted to minimize the sum of all alpha values plus k times Z. So first let's look at this particular value. For any edge in the matching M, when we look at alpha A plus alpha B plus Z, in fact twice n minus 1 minus 2 n minus 1 get cancelled, similarly minus 2i plus 2i get cancelled, we get 0. So k times Z plus sum of all the alpha values, because alpha u is 0 for all unmatched M, we can nicely group them together as follows, and that turns out to be 0, because for each edge in the matching we just showed it is 0. So if alpha is dual feasible, which is yet to be shown, it means the optimal value is at most 0, because there is a dual feasible solution whose objective function value evaluates to 0. It's a minimization LP, so the optimal value is either 0 or if anything less than 0. So this was our assignment of alpha values and Z. So all these properties, that within each level the matching is stable, any edge that goes one level below the weight is minus 2, there is no steep edge, all this will actually imply that for every edge we have alpha A plus alpha B plus Z is at most weight of the edge. It's exactly the same as what we did in detail towards the end of last lecture, some 5 different cases. We just have to do the same exercise all over again. So trust me, alpha Z is dual feasible, and we showed the optimal value of the dual LP is at most 0, hence M is a popular maximum matching. So that's what I wanted to do in the first half of this talk. Is it okay so far? So I've sort of hand waved many details, but it's all in the same spirit as in the last talk. Now I wanted to shift focus from the two-sided preferences to one-sided preferences. So actually popular matching algorithms, so though the notion of popularity was defined, like as I said 50 years ago by Garden-Force, who observed that every stable matching is popular. So stable matchings and two-sided preferences, that's what we have seen so far. But originally popular matching algorithms were first studied in the model of one-sided preferences. That's why I am comfortable calling these vertices agents. These are agents, and these were actually called objects or items. So agents have preferences over items. Items have no preferences. And this is also called a house allocation instance. So these are people who want houses, these are houses. Houses have no preferences. So this model was considered in several government house allocation schemes. And this is also a well studied model. So we say a matching M defeats matching N, or is more popular than matching N if we count only votes of agents, because items have no preferences, they have no votes also.
Agents have priority.
I'm sorry?
Do agents have priority?
No, all agents have the same priority. Yeah. So we can in fact look at a more general model, but let's stick with the simpler model. So his question was, are some agents of higher priority and some agents of lower priority? We'll say everybody has the same priority. And in fact, we have also considered ties in preferences, if you have noticed. So we are in this model of one-sided preferences and we have also allowed for ties in preferences. And when we compare two matchings, we only count the votes of agents. And we go back to the problem that we saw with weak Condorcet winners. When we hold elections between pairs of matchings, in fact, there can be cycles. So let's look at this instance where there are three agents, A0, A1, A2, and all of them have the same preference order. B0 is the top choice, B1 is the second choice, B2 is the third choice. So I have considered three different perfect matchings here. One is a blue matching, one is a green matching, one is a red matching. Is there a popular matching here? We want to claim there is no popular matching. Let's look at elections between the green and blue matchings, for instance. So the green matching wins 2 votes, the votes of A1 and A2. Both A1 and A2 prefer the green matching to the blue matching. Why is this? Yeah. So just compare. And when we hold elections between the red and green matchings, the red matching is more popular than the green matching. And when we hold elections between the blue and red, blue is more popular than the red matching. So we have blue defeats red, defeats green, defeats blue. So for every matching here, there is a more popular matching. So this instance has no popular matching. So the question to study here is, given such an instance with one-sided preferences, and it's got nothing to do with ties and preferences. The example we considered, there were in fact strict preferences, nevertheless there was a cycle. Given an instance, does it have a popular matching? If so, find one. So in fact, the first algorithmic question studied in the popular matching domain was a polynomial time algorithm to solve this problem. That was several years ago. In 2005 was a conference version, 7 is a journal version. However, there are a couple of issues here. So this algorithm is quite good. It works even when there are ties and preferences. However, it does not generalize to something that are more general called partial order preferences. So partial order preferences are the indifference relation need not be transitive. So maybe I don't have time to go through all that now, so just take it from me. It works even when there are ties and preferences, but for something called partial order preferences that are more general. So the preferences form a partial order. Just take it as this kind of general, that's a general definition of partial order preferences. It doesn't work for partial order preferences, and more importantly, it does not seem to extend to solve the popular maximum matching problem. So our goal here is, as we saw with two-sided preferences, we want to solve the popular maximum matching problem. And just the way the red-blue algorithm generalized nicely into a colorful version that solved the popular maximum matching problem, it would have been nice if this algorithm generalized to solve the popular maximum matching algorithm, but at least we couldn't see how to generalize it to solve the popular maximum matching problem. So let's focus on this problem, the popular maximum matching problem in one-sided preferences. So since we assume that the input can have ties and so on, actually we can assume without loss of generality that G has a perfect matching. So perfect matching, that's an assignment. So we can just add some dummy nodes by adding some dummy agents and artificial items. Assume without loss of generality that G has a perfect matching, that's an assignment. And the popular assignment problem is, given an instance with one-sided preferences, does it admit a popular perfect matching, a popular assignment? And in fact, again it's easy to justify that this is a generalization of the popular matching problem. And as I said, agents have something more general than just ties in preferences, they have partial order preferences. So we'll show an algorithm for this problem. It's a combinatorial algorithm, but it's actually based on the LP method, that what we've been seeing in the last two algorithms. So the original algorithm, the one for the popular matching problem, is based on a very clean, a very nice combinatorial structural characterization of popular matchings. We don't have such a combinatorial characterization of popular assignments. So this problem certainly seems more difficult. Nevertheless, this is a polynomial time algorithm, And since we couldn't come up with a combinatorial characterization, you know, the LP method really, that's the answer here to virtually everything that we consider. So again, what does the LP method use? It uses a weight function. Now rather than +2, -2, 0, our weights are all +1, -1, 0 because it's only one side that has preferences. So the weight of an edge AB is +1 if A prefers B to its partner in M, it's -1 if A prefers its partner in M to B, and it's 0 if B and its partner are tied in A's preference order. So for any perfect matching, the way we define the edge weight function, the weight of any perfect matching under this edge weight function is the sum of weights of edges in the perfect matching, and by definition it just follows that it's the difference between the number of votes that N gets and M gets in the head to head election. So M is a popular assignment if and only if the weight of every assignment under this edge weight function is at most 0. So let's write the LP for max weight perfect matching. That's a very nice and simple LP. So M is popular if and only if the optimal value of this LP is at most 0. Now you all know the algorithm. What do we do next? We write the dual. So the dual LP is very simple. We have one dual variable for every constraint, alpha u, and it's unconstrained because this is an equality. So every edge has to be covered. So M is popular if and only if the optimal value of the dual LP is at most 0. So I've just rewritten the dual LP. M is popular if and only if there exists a dual feasible solution such that the sum of all the alpha values is 0 and every edge is covered. And we show there is always has an integral solution. So there is always a nice structured dual feasible solution. So this is not hard to prove, but we'll take it for granted. There exists a dual feasible solution alpha such that alpha values of agents are 0, 2, 0, 1, 2 till n minus 1, and alpha values of items are 0, -1, -2 and so on and so forth. So I have again gone back to using colors here because it's a good intuition to keep. It was that algorithm that motivated this algorithm actually. So it's good to go back to that colorful graph G star and these colors somehow. Though I am calling them 0, 1, 2, they were all in a way inspired by the colorful graph. But the colorful graph and so on was in the world of two-sided preferences. This is one-sided preferences. So our goal is to come up with, so we don't even have an algorithm, but we know the proof of popularity is if we show such a dual feasible solution. So the alpha values of items are 0, -1, -2, and the alpha values of agents are non-negative values. But let's first think of a coloring function for the items. So suppose there is a coloring function on items and every item gets one of these colors. Let's define a subgraph G sub C where C is this coloring function as follows. For every agent, let C star of A be the maximum value of a color in its neighborhood set. So for every agent, getting as high a color as possible is better. So let's say agents like higher colors, n minus 1 is the best color, n minus 2 is the second best color and so on and so forth. So for every agent A, let's define C star A to be the maximum value of a color of its neighbor. So given any color function, let's come up with this C star A, and the edge set EC of GC consists of these edges. So every agent keeps edges to those neighbors B that have the best color, and among all its neighbors in the best color, B is the most preferred one. And it also keeps edges to items that are colored one less color, and B is the most preferred neighbor for A in the second best color, and moreover A has to prefer B to all neighbors in the highest color class. So rather than go through all these words, let's see it in an example. So let us look at this agent A1. It has neighbors in 3 different colors: purple, green and blue. So the highest color is purple, color 2. So C star of A1 is 2. For A2 it has neighbors only in 2 colors and the highest color is 1. So for sure A1 has the bold edge to this, to the top neighbor which is in color 2. And when it looks at one less color, that is color 1, so these numbers 1, 2, 3 are the preferences. It does not prefer its neighbor in color 1 to its neighbor in color 2. So I have kept this as a dashed edge. This edge is not in our subgraph G sub C. And this edge, though it is the top choice, it is not in an allowed color. It is allowed to keep edges only to the highest color and highest minus 1 color. So you must say, how did you come up with all this? Well, we will see. It is all the linear program, the dual LP that came up, that helped us to come up with all these conditions. Let us look at A2. A2 keeps for sure the bold edge, that is the only top maximum color edge in its neighborhood. It also looks at one less color, that is color blue, and both these neighbors are strictly preferred to this neighbor. So these are rank 1 edges which are more preferred to rank 2 edge. So A2 prefers its neighbors in color blue or color 0 to its neighbor in color 1. So all the blue edges are in this subgraph and the dashed edges are not. So, and if in this subgraph there is a perfect matching, then we can show that this matching is a popular assignment in the original graph G. So putting everything together, if there exists a nice coloring to the items such that this subgraph, where we defined the subgraph in the previous slide, admits a perfect matching, then in fact that is a popular assignment. And basically such a coloring implies a popular assignment, and conversely if there is a popular assignment, we can show a coloring so that the corresponding subgraph GC admits a perfect matching. So our whole problem is find such a coloring to items if there exists one. So I think I am already going over time, so let me just flash the algorithm. So let us start with every item getting colored 0. The subgraph GC in this case is easy to define. Every agent just keeps edges to its most preferred object because everybody is in the bottommost color. If there is a perfect matching, it means every agent is getting a top choice item. Well and good, just return the matching. Well, if there is no perfect matching, then for every unmatched item, increase its color. And if it is the case that there is an item that is getting colored n is not an allowed color, all the colors have to be from 0 to n minus 1. If there is an item getting color n, then return no, there is no popular assignment. Else, if all the colors are in the allowed range, go back to step 2, your subgraph has changed because your coloring has changed. Again look to find a maximum matching in the subgraph. If the maximum matching is perfect, the story ends happily, return M. If it is not perfect, there are some unmatched items, increase their color, check if any color has exceeded the allowed range. If it has exceeded, the answer is no. If it has not exceeded, go back to step 2. So in fact, it is a rather simple algorithm. So either a perfect matching in GC is returned, or the color of some vertex has gone into the forbidden range, it's become n. So when a perfect matching is returned, we use these colors on items to show a dual certificate, and that will prove that the resulting matching is indeed a popular assignment. And in the other case, if the color of any object has become n, we show G has no popular assignment. It is not that our algorithm failed to find one, but it is actually the case that G has no popular assignment. And this algorithm works for partial order preferences, and in fact this is a nice generalization of another popular matching algorithm. So the original popular matching algorithm was different. So this is another algorithm, and when we restrict the number of colors to 2, or let there be n colors, but as soon as the color of any object becomes 2, if we say no, that becomes an algorithm for the popular matching problem. So this is in the same spirit as the red-blue graph versus the colorful graph. So here let's use n colors, but the minute any color becomes 2, we say no, that solves the popular matching problem. And when we say the minute any color becomes n, we'll stop, that becomes the popular maximum matching algorithm. So let me stop now. I made several more slides, but let's not get into it because it's your poster session now. So this was joint work with my collaborators. So maybe I should just go through this thing just to show the last slide where I have to mention my collaborators. So the original popular matching algorithm from 2007 is with these collaborators. What is the red-blue graph, colorful graph was from this paper, and what we saw just now, the popular assignment algorithm, was from this paper. And I just wanted to spend the last slide on how this whole notion generalizes to something more general. This is in the setting of matroids that would have involved a lot more vocabulary. That was with other collaborators. Thank you.
Thank you, ma'am, for this session. So now we will